Alright, hi, welcome back to my YouTube channel. Today I'll be filming and recording me deriving the maximum angular frequency in a cylinder when big R and little r are basically equal to each other, so it can make this problem more simple. To start this off, I drew some diagrams to help us visualize what's going on here. So basically what we're going to have to find is what is the max spill of a cylinder. So right here's our cylinder, and here's like the top of the cylinder where the spill would occur. And we need to draw a line here, figuring out where the spill would be, like where it would come at. And let's just say it's like right there, because it's all like theoretical and arbitrary points. But let's just say it's right there. And then from that we can write out the equation. Well, first let's define our little cylinder here. So basically h is the height right here, right through here. And r is down here, and r is right there. In a normal problem, the two r, we won't get so fortunate where the r's are the same, but this problem is made simple for us to solve, so we can figure it out better. So from there we have the r and that r, and then we could write h is equal to the r minus distance plus hr, the height of r. And then we're going to be able to, we'll come back to this equation later. But basically that's it right now that we'll use. So to start this equation off, we're going to be looking at the change in pressure over the change in radius. So when we look at that, the change in pressure of the change in radius equal to rho, we'll be looking at the change in pressure over the change in radius times the density times the angular velocity squared times the radius. So what we're going to do is we're going to integrate the dP and the dr, the change in r, the change in pressure and the change in r. So from here we're going to get from 0 to p, dP, change in pressure, take out the density times angular frequency, and then integrate from 0 to r dr. This is just going to be p, and this is going to be r squared over 2. Now we know earlier that, from earlier on in our class, that pressure is equal to density times gravity times height. And we want to find the height right now from this equation. So what we're going to do is we're going to equal the pressure to density times gravity times height. So we can solve for h. Now we know those are going to cancel. So we're just going to get h is equal to w squared r squared all over 2g. Now from here, we can start figuring out, from here we're going to have to integrate and find the volume of the equation, which we already given this equation from earlier on. And what this equation is the change in volume times the height times 2 pi, this is from the volume of the cylinder this equation comes from, times 2 pi r dr. It's like the area of the cylinder, or the volume of the cylinder, my bad. So from this we can sub in our h value, we get dV equal to w squared r squared 2g times 2 pi r dr. Now from here, what do we want to do? We want to integrate the dV, and we can integrate the r dr here, the change in radius. So what we're going to do is from 0 to v dV, change in volume, and then we're going to have to, so this is just going to be canceled, so r squared dr from 0 to r. And then from this would just be v, and this is going to be 2g 2 pi r to the 4th over r to the 4th. And that will be our v value. That will be our v value. So from here we get v is equal to w squared 8g 2 pi over R4. Now, from here, we're going to have to pi r d. So now we need to find the distance so we need to get this equation, but how are we going to get there? So we need to find d now. We know v. We know this part of the cup when it was like flowing around before it spilled. We know the volume is pi r squared times d equal volume. So we know the volume now. So from here we can do, I'm going to erase this real quick. Keep the b part. Alright, so we know the volume right here. So v is equal to pi r squared d. V is that. So we have 2pw squared r4 over 8 pi equal pi r squared d. Okay, so now we just cancel the variables, so that would be that. So this would just be, okay, and that would become that would be d. Now from our equation, from this equation, we now substitute in to find the max angular velocity, the maximum in the cylinder. So what we're going to do is we're going to have h equal r minus d plus hr. So from here, the height times radius minus distance plus the change in height times r, because r is equal to, little r and big R are equal to each other because that's how the problem was made. So it doesn't really matter what the r looks like because they're equal. So from here we can get h minus r equal minus d plus hr. So now we know that d is this. That canceled. So now we can look at, so now we just solve for w squared, or angular velocity squared. So to do this we do h minus r times 4g divided by r squared equal w. And that is the maximum angular velocity in the problem for a cylinder with the same r, little r is equal to big R. This problem would be a lot more harder if that was the case, if little r was not equal to big R. But since that was not the case, it was really easy to solve. Thank you for coming to watch my YouTube video today, and that's all.